Just
So,
waiting for recording to get started.
okay.
Yeah, we can start, right? The recording starts.
Yeah, I mean, I have pressed that start recording, but okay, now the recording is on. All right, great. Okay, so hi, welcome everyone. In today's research seminar series, we have the presentation by Jyotirmoy Sarkar, and its title is Postulating Explanatory Habitability via a Novel Anomaly Detection Method. His advisors are Professor Snehanshu Saha and Professor Shantanu Sarkar. The lightning talk is by Yogesh. His title is Finding Shortest Paths by Analyzing Cost Surfaces. His advisor is Professor Vinayak Naik. And the second lightning talk is by Swapna. Her title is Study of the Thalamocortical Dynamics in the Visual Pathway Using In Silico Model. And her advisor is Professor Basavdatta Bhattacharya. Okay, over to you, Jyotirmoy.
Okay, thank you. So let me share my screen.
Yeah, let me know when to start the timer.
Yep. So everybody can see my screen?
Yeah, it's coming up. Okay, we can see it now.
Okay. Yeah. So yeah, we can start the timer now.
All right. Yeah.
Yeah. So good evening, everyone. The topic which I'm going to discuss today is postulating exoplanetary habitability via a novel anomaly detection method. I am Jyotirmoy Sarkar, and my supervisors are Professor Snehanshu Saha and Professor Shantanu Sarkar. So let's move on to the outline section. So first I'll talk about the introduction section. Then I'll discuss about mimetic algorithms. Next topic will be experiment sections, and we'll conclude at the end. So let's discuss about the motivation part. So thousands of exoplanets are available in the galaxy. There is a famous physicist named Michio Kaku. Once he said that there is every 200 stars there is a single planet like Earth, and such stars are present in this galaxy 500 million. So 500 million are huge number, and if you want to scan all of them manually to identify what are the probable habitable planets, it will be tedious work. That's why we want to come up with a tool or screening tool or scanning tool which will help us to prioritize the probable habitable planets out there. So the approach which we are going to discuss is based on a hypothesis. The hypothesis says that the number of potential habitable exoplanets is significantly less than the non-habitable ones. These habitable candidates could be thought of as anomalies in the large pool of normal instances. For example, we have thousands of exoplanets available in this galaxy. So we can consider these exoplanets as normal instances, whereas the habitable planets are very rare in this galaxy. So we can consider habitable planets as an anomaly. Based on this hypothesis, we have applied the anomaly detection algorithm in habitable planet identification. Anomaly detection technique is very well known, and it has been applied on multiple domains such as fraud detection and machine failure identification and so on. Here we have applied anomaly detection to identify or cornering the probable habitable planets. So next we are going to discuss about the mimetic algorithms. Here we will discuss multi-stage mimetic algorithms. Before we jump into the algorithm, let's discuss about some of the terms frequently used in mimetic algorithms. So what is meme? Meme is a basic unit of cultures. So that is any idea or knowledge which can be passed from one person to another person by imitation. So what is the difference between mimetic and evolutionary algorithms? Mimetic algorithms are specifically meta-heuristic algorithms, and it is the hybridization of evolutionary algorithms. In case of mimetic algorithms, we inject inject information specific to the problem we are trying to solve. Otherwise, evolutionary algorithm would have taken longer time. We do hybridization because we want to accelerate to find the solution. So what is multi-stage mimetic algorithm? Here we have employed a multi-stage mimetic algorithms. Typically, mimetic algorithms involves a single rate of crossover, mutation, and fitness function. However, in case of multi-stage, we can employ different strategies in different stages. So we can have multiple crossover rate, mutation rate, and fitness function in MSMA. So let's discuss about the few of the terms which are frequently used in mimetic as well as evolutionary series algorithms. Crossover. So crossover is analogous to the biological crossover. Here, two chromosome sequence or solutions becomes a parent and exchange the genetic information to form a offspring. And the crossover rate can be vary from problem domain we are trying to address. Mutation rate also similar to the biological mutation. Here, one or multiple gene values alter their values from the initial state. For example, in the gene sequence, if the gene value is 1, it becomes 0, or it was 1, it was 0, then it becomes 1. And mutation rate also can vary from problem domain to problem domain. Then fitness function. Fitness function evaluates the fitness of the offspring of the solution we are trying to address. Say two parents exchange their genetic information and new offspring forms, and this we try to evaluate the fitness of the solution. In case the fitness values are very high, then the chances of survival will be high. So it is analogous to the survival of the fittest. So in case of MSMA algorithm, we employ different strategies. So we have omega 1, omega 2 to omega 4. For stage 1, we employ omega 1 to omega 2. And for stage 2, we have employed omega 3 to omega 4. Different breeding strategy and mutant strategy can be differ from stage to stage. So let's discuss about the initial gene pool on which the MSMB MCA algorithm works for. So MSMB MCA algorithm stands for multi-stage multi-version mimetic clustering algorithm, which belongs to the same class, which is a multi-stage mimetic algorithm. And here we have designed the initial gene pool in favor of clustering algorithms. So here the initial population, where you can see the rows are versions and the column represents the data points. For example, I have a data set which has 10 data points, and the data set there are 3 clusters are available, 3 classes are available. So first data point has been assigned in the first version to 0 cluster. Second data point has been assigned to first cluster. Third data point has been assigned to second cluster. In the second version, we have assigned first data point to 0, second data point to 0. Here the class got changed, and the third data point we have assigned to first cluster. Even here also class got changed. In the same fashion, we can create multiple version. So the MSMB MCA algorithm is going to apply on this initial gene pool. The gene pool has been designed in this fashion. So this is the algorithm. And here you can see we have employed 2 stages in this MSMB MCA algorithm, but however, you can employ multiple stages also. So in the first stage, we have employed omega 1, omega 2. In the second stage, we have employed omega 3, omega 4. Here we have employed fitness function. In the first stage is Silhouette, and in second stage we have employed Davis Baldwin. So these are purely clustering, purity metric fitness function. Since we are trying to solve a clustering problem, that's why we have employed a clustering purity metric as fitness function. At the end of this algorithm, will be receiving a particular version which has the highest fitness value. So next, discuss about the anomaly identifier algorithm. The entire anomaly detection process can be divided into 2 phases. First, the anomaly tree construction, and the second is the anomaly identification. First, we'll discuss how we construct the anomaly tree. So this is the anomaly tree algorithm. Here we define n as the tree level we are expecting in the anomaly tree. And MSMB MC algorithm internally has been used to split the incoming data set. First, it always split, since we are trying to build a binary tree, it will split into 2 child nodes. So individual child nodes again recursively call on the same algorithm, anomaly tree algorithm. At the end of this algorithm, it will return the entire anomaly tree. So how a anomaly tree looks like? It will be something look like this. So initial data set will be split into 2 clusters. Again, individual cluster C1 and C2 will be further clustered into 2 different nodes, C3, C4, and C2 will be C5, C6. So this is the recursive way of construction of the anomaly tree. But this anomaly tree does not tell anything about the anomalies. So, but using this anomaly tree, our algorithm will try to identify the anomalies. So next, we'll discuss about the process you employed to identify the anomalies. So we have employed EC below F, which is enhanced cluster based local outlier factor. So ECBLF, how does it work? ECBLF will divide all these clusters into two categories. Here we have C3, C4, C5, C6. Only the leaf nodes from the anomaly trees are participating in the anomaly identification. So all the data points present in the dataset will be part of any one of these cluster. So will based on a threshold, it will decide large cluster and small cluster. If the cluster size is less than the threshold, it will be a small cluster. If the cluster size is greater than this threshold, it will be a large cluster. Once it has segregated the clusters into two categories, it has employed two strategies to compute the anomaly score. For example, I have a data point P and I want to identify the anomaly score of P. So how to identify? If in case P belongs to Ci and Ci is a small cluster, then it will compute the distance between P and Cj. What is Cj? Cj is a large cluster, and say I have B number of large clusters. So it will compute the distance between P to all the large clusters, and the lowest distance will be considered as anomaly of P. In case P belongs to a cluster which is a large cluster, it will simply compute the distance between the cluster center where it belongs. So this is the way we compute the anomaly score of data point P. And ECBLOF is a semi-metric because it satisfies the non-degenerate and symmetric properties. However, it does not satisfy the triangle inequality. For any function to qualify as a metric, it has to satisfy all the three properties: non-degenerate, symmetric, and triangle inequality. In case it does not satisfy the triangle inequality, so it is a semi-metric function. So next, move to the Msm Bti algorithm. So using the dataset, it will first form the anomaly tree. From the anomaly trees, it will identify all the leaf nodes. So once it identifies the leaf nodes, it will apply the ECBLOF on the leaf nodes to identify the anomaly score of individual data points. After identifying the individual data point, these functions will be applied to sort the data instances based on anomaly scores in descending order. Data instances with higher anomaly scores take the top position, means which is taking the highest rank would be considered as higher anomalies. It will be higher probable anomalies. So only the higher anomaly scores data points will be written at the end of this algorithm. So we are computing the probable anomaly data points using this algorithm. So let's discuss about the experiments we have done using these algorithms. For Msm MCA, we have considered Rand and Jaccard coefficients. So Rand and Jaccard coefficients are very well known for clustering performance evaluation. Rand index is computes the similarity between two different data sets, and Jaccard also identifies the similarity as well as the diversity between the sample data sets. And Jaccard index, it's sometimes called Jaccard coefficients, which is between 0 to 1. And Msm Bti has been used mean, max, range, mean, and STD depth. Mean means it is the lowest anomaly rank of all the anomalous planets present in the dataset. Max is the maximum anomaly rank present for all the anomalous planet. Range is minimum and maximum rank. Maximum range, the range it will define, and mean is the average rank, anomaly rank of all the planets, and standard deviation also implies the standard deviation of all the anomalous planets. So first discuss about the MSMB MCA performance. So MSMB MCA has been applied on 6 different benchmark datasets: IRIS, GLASS, SEED, Knowledge, Libras, and Sonar. These are well-known benchmark datasets for clustering, evaluation of clustering algorithms. And we have compared to well-known clustering algorithms, K-means and K-medoids. So IRIS is a dataset which has, I think, around 150 data points and 3 clusters. Each cluster has 50 data points. And IRIS MSMB MCA has given Rand index as 0.91 and Jaccard has given 0.93, whereas K-means has given 0.87 and Jaccard is 0.44, which means that MSMB has produced better result here. In case of SEED also you can see MSMB MC has produced 0.95 and Jaccard is 0.33, whereas K-medoids has shown 0.87 and Jaccard is 0.27. So overall, if you see that MSMB has shown better result here. And let's discuss about the MSMB BTI result. So Msm Bti has been applied on two different dataset D1 and D2. They have been collected from PHL catalog dataset. PHL is the catalog which captures all the exoplanets information. And out of the D1 dataset has 1,682 exoplanets. Out of that, 51 are anomalies. 51 anomalies mean they are the probable habitable planets. And we have compared this LOF, KNN, HBOS, and isolation forest. And if you see, in case of mean, this HBOS has shown the lowest rank, which is 9, and MSMBT is 14. But however, in case of max, MSMBT has shown the lowest rank, which is 664. In case of LOF, it is 1,485, and isolation forest, it is 763. In case of mean, we can see the average anomaly rank of the anomalous planets are 215 for MSMBT, which is the lowest, and 440 for LOF. And the standard deviation also I can see it is the 175 for MSM Bti, and HBOS it is 329. In case of range, we can see MSM Bti has the lowest range. It has cornered within a smaller span, and in case of LOF, it has 16 to 1485, which is a bigger range here for LOF. So let's move to the next slide. Here we have employed D2 dataset, which contains 706 exoplanets. Out of them, six are anomalies. We have a data processing also. Many features having any missing data. We have discarded those features, only kept those features which are having records for all the planets. So all the 6 planets has been shown in this table, and you can see that in case of mean also MSM Bti has shown 46, and whereas in LOF has shown 67, and max MSM Bti has shown for 85. However, HV has shown 213. In case of mean and max, both MSM Bti shown lowest rank. And in case of mean and standard deviation, if we see this isolation forest is 77 and 27, whereas MSM Bti has 66 15. Both are lowest in case of MSM Bti. In case of range, if we see, it is the lowest in case of MSM Bti, which is 46 to 85, around 40, the range. In case of
a little under 5 minutes remaining.
Okay. So in case of range LOF, you can see that it is 67 to 174. In isolation forest, it is 55 to 132, which is range is around 80. So let's discuss about the conclusion part. So we have identified few of the points which we think should consider as a part of future work. The first is the computation cost of MSMB MCA. Since it is a multi-staged multi-version clustering algorithm, it has employed multiple stages and multiple crossover and fitness functions. So the computation cost is it is a heavy. It has a higher computation cost in case of in comparison to other clustering algorithms. And we have shown or applied only MSMB MBCA in the domain of a habitable planet identification, but it is possible to apply this clustering algorithm in other domains to identify, emphasize its strength. In bibliography, this is the URL for planetary habitable classification. It has contains all the exoplanets information, and from here we have taken the datasets D1 and D2, where we have employed this, where we have experimented our proposed algorithm. Yeah, thank you. So, any question?
Great, thanks, Jyotirmay. You ended well in time. We'll take questions at the end.
Okay, sure. Thank you.
Right. Over to Yogesh then.
Hello, am I audible?
Yes, Yogesh, you're audible.
Firstly, thank you everyone for attending this talk. Okay.
Yeah, so, just 1 second. I'll start a timer for 3 minutes and warn you when 1 minute is remaining. Okay.
Okay.
Okay, you can start.
Okay. So we already know that the shortest pathfinding problem, it is a classical problem which is NP-hard, and the reason is because of the nature of the obstacles and the environment. Because of that, it is an NP-hard problem. So for any shortest pathfinding problem, what do we need is we need a graph for that. So that we need to represent the real world in a form of a graph. Once we have the graph, we can then apply any pathfinding algorithm to traverse the route to the shortest path. So, so the currently the most popular solution is the nav mesh solution approach, wherein we can we have a 3D model of the building, and then we can make a graph, convert it into a graph. Now the problem with that is like how deep the graph should be. Like why do we have a nav mesh? Is like because it can store more information as compared to other methods. So now what is the problem with that is if we have if you can see the four things over here, if you have a dense graph, the thing is to generate that graph it takes more time, whereas if you have a smaller graph it will take less time, but the thing is you won't be able to find the shortest path, for example the D part over here, whereas if the A figure over here you will be able to get the shortest path quickly, but the time to generate it as well as the memory is exponential. So and the second thing, once you have found the graph, uh, then you have to apply the shortest path algorithm. And the most widely used algorithm currently is the A star. So any optimized versions of A star also will be referring to as A star only. So then the advantage of A star is being simplistic, and then it is used in embedded systems and other things because of its the way the memory it takes is less. But the thing is, what happens is it needs two conditions. Like in order to find an optimal solution, the heuristics selected has to be admissible. So as a reason, you can see over here like this is from the start to the goal. You have the path over here, but it has expanded more. The search space is like it has expanded more nodes, so that each processing each node will take some time. So again, we can do better in both these areas. Like so. So in our approach, we are making use like if you can observe this, the start to the end, this pink line. So it is kind of a resembles the flow of the water. Okay, so we have some more flow of a stream. So we have our solution.
Little under a minute remaining.
Yeah, so our solution is based on that. So it is in detail. In the final, we get the various steps, and finally we get the stream. And like so, the graph generation time, which was actually exponential, now becomes like it's a polynomial time, uh, and again the pathfinding time is also better. So I'll just give you one like example of it, like. Uh, so yeah, consider these are two agents. Like one of the agents, the one in the green over here, is is the agent where we are giving it our algorithm, and this the pink color capsule over here is the agent which is using the A star algorithm, and we told it to find the nearest point where to evacuate, for example, for any exit point. So they both started off and in real time, and yeah, so one thing over here, as you can notice, is that uh, yes, so the A star over here algorithm just faltered a bit because it thought the shortest path as per the heuristics. For example, the Euclidean distance, it thought this would be the closer, but then it turned out to be actually there are walls over here. So this is a small room. So it actually had to backtrack and then go back. Whereas our solution has found I mean the evacuation point faster than that. So these are the benefits of using it. Plus, the additional benefits are that the battery life and all the other things, the processing time and all that is lesser in this solution. So, thank you for that.
Right. Thanks, Yogesh. And over to you, Swapna.
Thank you. Just share my screen. Is my screen visible?
Yeah, it's visible. Let me know when I can start the timer.
Yeah, okay. Yeah, I think you can start, yeah.
Okay, I'll warn you when 1 minute is remaining.
Okay. Yeah, so today I'll be briefing you with the highlights of the study that we have conducted to understand the thalamocortical dynamics in the visual pathway using in silico model. My guide is Dr. Msm Bhattacharya, and this work has been recently been published in the Neurocomputing Journal of elsewhere, as well as in Bernstein Conference of 2021. So what are in silico models? In silico models are computational models that can be used to represent brain regions, and we can use that to then study the underlying dynamics and its function. So we have a in silico model of the visual pathway, where we give the retinal input, and this input is then processed by the lateral geniculate nuclei, and the sorry about that. Yeah, so the lateral geniculate nuclei will be passing on the information to the cortex, which is represented by layer 4 and layer 6. We have two types of input: excitatory, which will excite the neurons, and inhibitory, which will inhibit its actions. Besides the retinal input, we also have symmetrical inhibitory input and asymmetrical excitatory input from the rest of the brain. So we wanted to validate this model against experimental data, and we have chosen Nordbaum et al. 2016 experiment, where they conducted an Eeg experiment, where the human subjects were asked to look at visual stimuli of periodic and jittered nature, and their steady state visual evoke potentials were captured, which is the output of the EEG. It's SSVP called in short, we call it SSVP. So what they have observed over there is that when the input is periodic in nature, the frequency that gets that is seen in the SSVP responses is same as that of the input stimuli. So this is a case of entrainment of the brain rhythms by an external stimuli. So to validate. Okay, to simulate this case, we fed in input, retinal input of periodic jittered and noisy nature, and we did a frequency analysis of this of the output from the LGN as well as the cortex, and we found that only when the input was when periodic, during that time window, the frequency of the output matched with the input frequency, and the same was seen both at the LGN as well as at the cortical layers. Besides that, the phase locking analysis was done, and we see a very high phase locking when the input is periodic. So in general, we were able to validate our in silico model with experimental data, as well as simulate the phase entrainment conditions of SSVP. That's all. Thank you.
Great. Thank you so much. All right. Now we open up for questions. Audience, if you have any questions for any of the speakers, please unmute and ask. All right. Swapna, I think you are still sharing your screen. Are there any questions? All right. Oh, let me see. I think there is something on chat. Okay, no, it's all Dr. Snehanshu. Okay. Yeah. Great. Thank you, guys. So next week is the last week of our presentation series, and what we have decided is we can meet in person. So we'll be meeting in the department conference room, and I'll circulate an email about that. I'll also circulate an RSVP. The department has agreed to provide some snacks, so we need to get an idea of the number of people participating. So look out for a email and a form from me sometime soon. Okay, it will be a nice culmination. Okay, is there any 100% attendance award? Yeah, you are awarded with knowledge. Okay. Anyway, jokes apart, yeah, it was nice to see a lot of good participation from faculty as well as from different PhD scholars throughout the semester. But anyway, coming to next week, yeah. So and I had written to some PhD students who could not present, and I have heard from them. In fact, I heard from someone just a couple days back. I'll see how many of them we can accommodate. Um, Even if the presenters are remote, those who are on campus, we can get together and meet and it will be a nice culmination of the whole CSIS research seminar series. So thanks again for participating, and hope to see you all next week. Okay, thank you. Goodbye. Have a nice day.
Thank you.
Thank you.